Today we're going to take yesterday's lesson up just a notch and talk about linear programming, which is basically solving systems of inequalities with applications or word problems. Let's start out with just a review of yesterday first. We're going to graph this system over here. So if I want to graph x is greater than 2 but less than 10, that's actually two lines. And we know they're vertical, so I'll start at 2, draw a line straight down, and then count over to 10, 4, 5, 6, 7, 8, 9, 10, draw a line straight down here. Great. Next, I want to take and find the intercepts for this line. I could put it in slope-intercept form, but as you're going to see later in the lesson, we're going to get some really big numbers, and slope-intercept's not going to be as accurate, if you will, for the graphs that we're trying to do. So I want to find my x-intercept and my y-intercept, which means I set y equal to 0 for my x-intercept, x equal to 0 for my y-intercept. When I set y equal to 0, I get 2x is equal to 12, so 6 equals x. And when I set x equal to 0, I get 3 for my y. So now I have 2 points, and we'll do those in blue, I guess. So let's go over 6, 2, 4, 6, put a dot there, and then 1, 2, 3, put a dot there, and then I'm going to take and connect those points so that I've got a line, and that, so. And then we want y is greater than or equal to 0, so that's the horizontal line on the axis, like such, right? And what I'm going to do is I'm going to take and graph all these by shading the appropriate region. So this says find all values between 2 and -2 for x. So that's basically everything between these two lines. So I'll just shade all this here. It's even this part right over here. And then the next is I need to pick a sample point such that if I check 0, 0 for this slanted line, see if that works, is 0 plus 0 less than or equal to 12, and that's true, so it's everything under here, so I'll do that green. And then y is greater than 0, so that's everything up, so my shaded region is this triangle right here. And then what I'm going to want to do is find the vertices, and I can pretty much count all these, so I've got 2, 0, I've got 1, 6, 0, and I've done this pretty accurately so I can find the exact point, and I know the x value here is 2. So if I know my x value is 2, I say 2 times 2 plus 4y equals 12. Bring that over. 8 equals 4y. Y equals 2. So I did a pretty accurate graph. So this point here is the point 2, 2. And the additional information we're going to talk today is, given something called an objective function, find its maximum value. They're going to give us this equation, f of xy, which means it's a function with x and y in it. So they're going to use this equation to try and find a maximum of this shaded region, or what we call the feasible region, where our answer should be for our system. And it turns out that even though there's infinitely many points within this region, our maximum and minimum values are only going to occur at these vertices, which we've already found. So let's plug those into this equation. If I plug in 2, 0, I get 3 times 2 minus 7 times 0, which equals 6. When I plug in 6, 0, 6 times 3 minus 7 times 0, which is 18. And I plug in 2, 2. I get 3 times 2 minus 7 times 2, which equals negative 8. So in this case, I have maximum value of 18, and that solved the problem. Now, this is the process behind linear programming, except for the fact that these equations were already given to us. Linear programming is going to involve getting an application and then making those equations up. So let's take a look at a sample linear programming problem. Here's what your basic linear programming problem is going to look like. It's a word problem. And in this case, we have 44 planes available on a given day during an airlift. Some planes are large and some are small. Large planes require 4-person crews. Small planes require 2-person crews. Selected from a total of 128 crew people. Large planes carry about 30,000 cubic feet, while the small planes only carry 20,000, and we want to know how many of each type of planes are needed to maximize cargo space. Every one of these linear programming problems is going to have a maximizing or minimizing aspect to it. So the steps we want to take to solve this are as follows. So the first thing we want to do is find an objective function and write that down. And we look for the maximizing and minimizing part. And that happens to be right here. And we're maximizing cargo space. So I look for the cargo space information and I see it right here and right here. It says the large plane, so I'm going to call the large X and the small Y. So I know that I'm trying to find a maximum value for 30,000 for every large plane X and 20,000 for every small plane Y. That's my objective function. Then the next thing you want to do is identify something called constraints. Now constraints are limitations to what we can use in the problem. So if I read through, I know this is a limitation. I've got 44 planes. And then I've got another limitation right here of 128 crew. So I've got 44 planes I can use and 128 crew. Now, I know I can't go over either one of these, so I must be less than or equal in both cases. Next, we need to write an equation that deals with these constraints. So it doesn't give me any comparison of large planes to small planes, only that I've got 44 planes in all. So that means if I take and add the two, x plus y, that means the large planes plus the small planes are less than or equal to 44. Now, it tells me a little about the crew. It tells me that the large planes take 4 crew members each and the small planes take 2 crew members each. So I can write an equation that says 4 for every large plane and 2 for every small plane. And if I add those up, I get less than or equal to 128. So these are my constraint equations relative to the problem. And next I'm asked to go ahead and graph. So we're going to graph these by taking and once again probably finding intercepts. I think that's probably the easiest way to go, so let's do that. This is 44 and 0 and 0 and 44 and plug 0 into this. For y, I get x out of 32, and if I plug 0 in for x, I get 64. So now we're going to graph these points. Another thing we probably have to know is that x has got to be greater than or equal to 0. We're probably going to use some planes, and y is going to be greater than or equal to 0. So that's the two axes. So let's go ahead and graph those now. And I'll scale this appropriately. So I'll go by 5. So every 2 is a 10, 20, 30. Scaling is kind of important so your graph isn't too small and you get proper intersections. So I'm going to graph 44 and 0, 0 and 44, that's roughly here and roughly here. I'll connect the dots on those in a minute. And then 32 and 0, around here, and 0 and 64, which is right around here. Go ahead and connect those dots. Here down to here. Drawing straight lines is pretty important too. Might be a good idea to have a ruler or some kind of a straight edge, and right around here. And then on each of these, we'll go ahead and do that sample point. And in the first case, my sample point will be 0, 0, just like the second case. 0 plus 0 less than 44 true, so I shade down. And 0 plus 0 less than 128, I shade down again. So as you can see, my double shaded region is all of this. So we look once again at our endpoints, and I have one here at 0 and 44. I have another one here at 32 and 0. This is 0, 0. And then I'm going to have to find this point right here. And it's not totally obvious to me what it is, so I'm going to solve the system. All right, I'll go over here to solve my system. It's the intersection of these two, so I have 4x plus 2y equals 128, and x plus y equals 44. Like we've done a couple days ago, I multiply by, let's go to negative 2, which gets me negative 2x minus 2y equal to negative 88. Add those up, that's 2x is equal to 40. So x equals 20. And then I plug back in to get y. Y equals 24. This is the point 20 and 24 approximately. And I need my maximizing equation. I'll write it again over here. I have 30,000 x plus 20,000 y equals max. 0, 0 gets me 0. 32, 0 gets me a total of 96,000. 0.44 gets me 88,000. And then 2024 gets me 1,080,000. So clearly, this is our maximum cargo space of 1,080,000 cubic feet with 20 large planes and 24 small planes. And that is basically linear programming from start to bottom. We're going to do another one just to show you. So once again, you can read through this I'll give you a second to do so. Our first step is to figure out what the maximizing or minimizing is going to look like. And you'll see that down in this bottom line, which is usually where this information is, it's either in the bottom or the top, is our minimizing, and we're minimizing costs. So I look at this 70 and this 30 as units of cost, and I look at what I'm trying to minimize, and it looks like protein powder from soybeans and protein powder from milk. So let's say our soybean is going to be our X, and our milk is going to be our Y. And we have 0.7X plus 0.3Y equals a min. And then we're going to take a look at our constraints, and it looks like we have at least 12 grams of this and 8 grams of this. So we have protein and carbs, and I throw this information down here and say I've got 12 of protein and 8 of carbs. However, in this case, we only have at least 12 and at least 8. So there could be more than each. So this is greater than or equal to, whereas our last problem was less than or equal to. And now what I want to do is I want to find information on protein powder. So protein powder has within it some protein and some carbohydrate. And that's the soybean type. And then I know my milk solid has 2 protein and 4 carbohydrates. So each type of powder has protein and carbs in it. I just want the protein information. So here's the protein information. 5 and 2. So I know in the soybean I have 5 for every soybean and 2 for every milk. Then I move over and I look for the carb information. And here's the carb, 3 and 4. So 3 for every soybean and 4 for every carb. And now I'm going to take and find intercepts for both of these. So this goes to 0 and 6 and 12/5 and 0. So it's not going to be super accurate, but I'll be close. And then the next one goes 0 and 2 and 8/3 and 0. And next, I probably ought to graph these, and we're going to need to make a decent scale. I'm going to go by halves. So let's go ahead and do that. So this is 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. And we'll go ahead and graph 0, 6. And then 12/5 is 2 and 2/5, which is less than 2.5, somewhere right around here. And then we'll graph 0, 2, and 2 and 1/3, or 2 and 2/3, which is a little over 2, so right around here. Notice the importance of that scale. If it was too small, we wouldn't be able to distinguish the 2 points. And then we're going to graph those. So I go from 6 to 2 and 2/5. And then I go from 2 to 2 and 2/3. So right around there. And then when I shade these, you'll notice the following. 0 plus 0 is greater than 12. That's not true, so I shade up. And then 0 plus 0 is not greater than 8, so I shade up again. And now my shaded region is on the outside, so color all this in. Up here, which means I have 3 points I need to look at. One is 6, 0, or 0, 6, I'm sorry. Another is this point right here, which is the bigger of the two x-intercepts, so that's 8/3 and 0. And then I'm going to need to find this other intersection point here, which is the intersection of these two lines. Once again, I'll solve that system. I have 5x plus 2y equals 12, and I have 3x plus 4y equals 8. Multiply the top by -2, -10x minus 4y equals -24. Add them up, gives me a -7x equals -16. So x equals 16 over 7. I'm going to have to find my y. And y ends up equaling roughly 2/7. So that's my third point. And I get 16 over 7 and 2/7. Now I'm going to plug that into my minimizing equation. 0.7x plus 0.3y is a min. And plugging 0, 6 in. 6 times 0.3 gives me 1.8. 8/3 times 0.7 gives me basically 1.87, so that's a little bit more. And 16/7 times 0.7 plus 0.3 times 2/7 is about 1.69. So there's your minimum value of 1.69 for 16/7 of a tablespoon of soybean and 2/7 of a tablespoon of the milk. Once again, pretty involved. Sure, we'll probably have to do an example tomorrow, but be clear on what you're confused about when we're writing our summaries, and we'll go at it again tomorrow. Thanks.